Hi, welcome to a video on half-life problems. This is related to exponential growth or decay, and in the half-life it relates to the decay part of exponential functions. The half-life of a substance is the amount of time for half of that substance to decay into other elements. For example, the half-life of plutonium-238 is 87.7 years. And this means that a sample containing 100 milligrams of P238 will contain half of that, or only 50 milligrams of P238 after 87.7 years. Then, in another 87 years, it will have decayed until only 25 milligrams of P238 remains, and then only 12.5 milligrams will remain after another 87.7 years, and so on. That plutonium-238, by the way, decays into uranium-234, which then again decays into something else, eventually into lead. So that's how half-lives work. Now this leads to the half-life formula A, the amount, equals A sub 0 of 0.5 to the T over H power, where A is the amount, T is the time, H is the half-life, or in this case, P238, where the initial amount's 100 milligrams and the half-life is 87.7 years, it gives us A of T is equal to 100, the initial amount, 0.5 to the T over 87.7. So we can use that formula to do calculations. So let's start with a sample containing 500 micrograms of tritium, which is left in a sealed container. The half-life of tritium is approximately 12.3 years. So how much tritium will remain after 24.6 years? Well, for this problem, I want you to notice that 24.6 years is 12.3 doubled, right? So this means that it will have undergone two half-lives. So after 12.3 years, the 500 milligrams will have become the 500 milligrams, micrograms, that's a millionth of a gram, will have decayed into 250 micrograms. That takes 12.3 years. And then in another 12.3 years, the 250 micrograms will have decayed until there's only 125 micrograms after another 12.3 years, which is 24.6 years. So our answer there should be 125 micrograms. Okay? So the next question is, how much tritium will remain after 30 years? Well, this is not quite so obvious as the 24.6 because it's not exactly two half-lives. It's two and then some. So just like in the first problem, we could have used the formula where after time we put in 24.6 years. We can use this formula too. So first of all, if we put in 24.6 in the first formula, 0.5 to the 24.6 over 12.3, this would have given us 500 times 0.5 to the second power. So we know there was exactly two half-lives, and that means we multiply by a half, once giving us 250 and then another time giving us 125. So that's what would have given us that. Now we have A of 30 years. Now there's notation. Typically our function notation, we put the argument in the parentheses there. You're going to be introduced to new notation where we use subscripting, and this is usually where we have sequences of numbers. But this, we're going to take A of 30 is equal to 500 times 0.5 to the 30 over 12.3. Now that 12.3 goes into 32 point something times. We're going to go ahead and use our calculator to do that calculation. 500 times 0.5, so we'll put in 500 times, and you don't really need a times sign if you put parentheses, but I'll just put times 0.5 to the power of. Now on my calculator it puts this up in the exponent, so I don't need parentheses around that numerator, or that exponent. 30 divided by 12.3. If you use a calculator that doesn't put those all up in the exponent, then you need to have parentheses around the 30 and the 12.3. So that gives us 92.204157, or I'm going to just say approximately 92. This is not exact. These aren't exact values. In fact, it didn't have an exact value to begin with. It just said 500 micrograms. So that's going to be, again, 92, about 92 micrograms would be our solution there. Okay. Now let's look at a little more challenging problem. Now we are given a sample containing 500 micrograms of tritium is still left in a sealed container, and we still have the half-life of tritium, 12.3 years. How long until the tritium remaining in the sample is only 50 micrograms? So before they gave us, using that formula, we had the formula A of T is equal to 500 times 0.5 to the T over 12.3, and they gave us that what T was either 24.6 or 30. But in this case, they're giving us the amount of the sample. So they're giving us, this is A of T, they're giving us what the amount should be. So they're saying 50 is equal to 500 to the 0.5 to the T over 12.3. So in this case now, we're going to use the, make that tip a little smaller. We're going to use logarithms to solve for the unknown in the exponent, which we have done in the past. So let's take this, and we're going to now divide both sides by that 500. First thing we do is divide by 500, and 50 divided by 500 is 0.1, or 1/10, right? That reduces to 1/10, which is 0.1, and that gives us 0.5 to the T over 12.3, that's a 12. And now we'll use logarithms. And so I tend to use the natural log. So I'll take the natural log of 0.1 is equal to the natural log of 0.5 to the T over 12.3. And using the natural log, we can take the exponent out and multiply it by that. That's 12. I'm just going to write it like this: 12 over 2 T over 12.3 times the natural log of 0.5. And now we can divide both sides by the natural log of 0.5. And we get T over 12.3 is equal to the natural log of 0.1 over the natural log of 0.5. And we could go ahead and calculate that. And that means we're going to multiply both sides by 12.3 to solve for this. So there's 12.3, and I'll put times 12.3 on this side. And we'll see that we get T, and I'm going to approximate that on the calculator. 12.3 times the natural log of 0.1 divided by natural log of 0.5. So that is going to be 12.3 times the natural log of 0.1. And notice that this prompted me a parenthesis there, so I'm going to have to close that parenthesis and then divide by the natural log of 0.5. And when it's the last parenthesis in a problem, you don't need it, but I'll put that parenthesis there, and that gives us 40.859. So I'm going to round that off to 41. That means it's going to be about 41, and that is years. That is about 41, approximately 41 years. Okay. Lastly, we're going to take a similar situation. a sample, the same sample, 500 micrograms, same half-life, 12.3 years for tritium. How long until only 5% of the tritium remains in the sample? So this is a good question. This means we start out, we could take 5% of 500 and, say that's 25, but you can also just say, you don't even need to know what the 500 is. If the remaining amount is 5%, we can put 0.05 there, is equal to the original amount. If it's 5%, the original amount would have to be 100% or 1. So 100% to 5% times 0.5 to the, and again, t over 12.3. So that gives us 1. We don't have to do anything. We could divide by 1 if we wanted, but that gives us 0.05. So we're going to take the natural log of both sides again. And so, again, we use the power rule that says I can multiply that exponent by the log. And now we'll be able to divide both sides by the natural log of 0.5. And we could really, at the same time, we could multiply by the 12.3 to eliminate the 12.3 in the denominator, times 12.3. So that's going to give us t by itself is equal to, and I'll write it this way, 12.3 times the natural log of 0.05 over the natural log of 0.5. And again, we'll use our calculator for that. Um, 12.3 times the natural log of 0.05 divided by, oops, I missed my parenthesis, didn't I? Divided by the natural log of 0.5. Notice on half-lives you're always going to divide by, I forgot my divide sign, didn't I? Second insert division. So you can insert a sign if you miss it. Enter, 53.159. So I'm going to say about 53 years. 53 years is the approximation. So that gives us kind of a summary of using logs in solving for the amount of time it takes for a certain amount of tritium to decay. And you can use this for any kind of radioactive substance or a substance that you know the half-life of. And so this 12.3 will change depending on what the half-life is. You do the same thing with things in the blood. It's called your blood half-life too. So anyway, I hope that this was helpful. That's all for now.